Hey everybody, so what we're going to talk about today are valence electrons and ions. If you have not done the 2.6 homework on ions, please do not watch this video yet. Please go do the 2.6 homework first and then come back and learn about valence electrons and ions. But if you have done 2.6, ready to go, learned about simple ion formation, now you are ready for this section here. So what are valence electrons? What are ions? What's the octet rule? What's all this good stuff we're going to talk about? So first things first, valence electrons are electrons that are in the outermost energy level of an atom. So valence electrons, you can abbreviate them VE with that little negative sign up there to show you we're talking about electrons. Valence electrons are the electrons in the highest or outermost energy level of an atom. So if we take a look at this Bohr model right here, stop and think to yourself, what's the highest energy level represented in this atom? Hopefully you screamed, N equals 3. That's exactly right. So N equals 3 is this outermost energy level here. So therefore, the electrons that are in that energy level are the valence electrons for this atom. This one, 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 and this one. So this thing has 8 valence electrons in that outermost energy level. The other thing you can do is try to figure out which Bohr model is this the element for. Ooh. Hopefully you said, it's argon. That's exactly right. It is. This is argon. Argon's Bohr model. Okay, so what's the big deal with valence electrons? Valence electrons are really important because that's really where your chemistry is going to happen. These are the electrons that are going to be lost if you're forming a cation, or it's the energy level that electrons are going to gain into if you're forming an anion. So take a look at the 3 Bohr models I have here for lithium, oxygen, and sodium. Pause this video and figure out how many valence electrons do each of these atoms have, then come on back. Okay, welcome back everybody. So lithium, if we're taking a look at the electrons in its outermost energy level, it has 1 electron in that N equals 2 energy level, so it's got 1 valence electron. Oxygen over here, it's got 6 valence electrons in the N equals 2 energy level. And sodium has 1 valence electron in the N equals 3 energy level. Okay, so what's the big deal with valence electrons and the periodic table? Remember, this whole unit has been about how are we organizing the periodic table. So take a look at these Bohr models for lithium and beryllium here. These atoms are in the same period, which means they are left to right of each other. Which period are these atoms in? The second, right beneath hydrogen in that second period here. So notice a pattern in these valence electrons. What do you notice about them? Lithium has 1, beryllium has 2. Take a second and predict to yourself, the next element in this period would be boron. What's the Bohr model for boron gonna look like? 1, 2, ooh, come on pen, 3. How many valence electrons does boron have? 1, 2, 3. So what's happening to the elements that are in the same period with their valence electrons? As you go across the period, the valence electron count increases by 1. So elements in the same period, as you go across the period, elements in the same period. Oh, actually, this is very redundant. Sorry. As you go across the period, I guess we can just say valence electron count increases by 1. Sorry to everyone who's writing this on paper and I made you erase that. My bad. So as you go across, valence electron count increases by 1 each new element. So if I scroll down to my periodic table here, I started out with lithium and beryllium, then I went over to boron. How many do you think carbon would have? 4. Nitrogen, 5. Oxygen, 6. Fluorine, 7. Neon, 8. That's exactly right. So on your periodic table, one of the things that I had you do was I had you renumber these columns. So this would be 3, 4, 5, 6, 7, 8. Remember, how many valence electrons does lithium have? Lithium had 1. Beryllium had 2. Boron had 3. Carbon would have 4. What are you noticing here? Not only does the count increase by 1, but the numbers that I had you label these groups with, that's the number of valence electrons. So group number matches valence electron count. Okay. If you want, you can also add that in to this column, or to this little row right here to help remind yourself. So as you go across the period, valence electron count increases by 1, and the valence electron number matches the number of the group. All right, how about elements that are in the same group? So lithium and sodium we've got here now. So lithium, which group is it in? It's in group 1. It has 1 valence electron. Sodium, which group is that in? This is also in group 1. It has 1 valence electron. Okay, so what's the pattern here? What are we noticing? Elements that are in the same group have the same number of valence electrons. Hydrogen, group 1, would have 1. Potassium, group 1, has 1. Rubidium, group 1, has 1. So everything in the same group has the same number of valence electrons. Oops, let's say as, come on pen, as you go down a group, valence electron count remains the same. So this makes sense, right? Valence electron count matches the group number. So everything in group 1 has 1 valence electron. As you go down that group, everything has 1 valence electron. Everything in group 2 has 2 valence electrons. So on your personal periodic table, what I want you to do is label the number of valence electrons in each group. I know this doesn't directly match your personal periodic table, but what you can do is you can just make yourself a little cheat sheet, number of valence electrons, put it in one color, and you'll say this one has 1, this one has 2, this one has 3, 4, so on and so forth. It matches the group number. But make sure you're doing it in the same color so that way you can keep track. Color coding is a really helpful way to do this. Okay, moving on to ions. So in 2.6, you learned about something called an ion. So why are these so important? First things first, what we're going to do is talk about something called the octet rule. If you think about oct, that as a prefix, what does that make you think of? Besides October and Halloween. Hopefully it makes you think of something like an octopus, right? An octopus has 8 legs, so the prefix oct here stands for 8. So all atoms are most stable. This means they are least reactive. So most stable is referring to least reactive. This is going to be super important when we do our lab next. When their highest energy level is completely filled with electrons. So think about what this would mean, their outermost energy level. If you had something like hydrogen and helium, how many electrons do those have? Hydrogen has 1, helium has 2. Where would those electrons show up in a Bohr model? They'd show up in n equals 1. Everything's lazy, designed to be in the lowest possible energy state. When is n equals 1 full? N equals 1 is full when it has 2 electrons inside that first energy level, because the first energy level can only hold 2 electrons. So hydrogen and helium want to become stable. Helium is incredibly stable. Helium's got those 2 valence electrons. So this doesn't match the prefix oct, though. 2 is not 8. So we say that helium obeys what's called the duet rule. Helium is most stable when it has 2 electrons in its outermost energy level, because its outermost energy level is n equals 1. For everything else, what did we say the other energy levels can hold? N equals 2. How many electrons fit in that one? This one holds 8 maximum. So that would mean that anything else is going to be most stable when it has 8 electrons filled in its outermost energy level. Now this matches that octet rule. So other atoms will obey the octet rule when their outermost energy level has 8 electrons in it. So all atoms are trying to get to this. They're trying to be most stable. They're trying to get their outermost energy level filled. And how do they do that? They ionize, or they bond. We'll learn about the different types of bonding in Unit 3, but for right now, what we're talking about is forming ions. So ions are atoms that have gained or lost electrons to become charged. Why can't we gain or lose protons? Those also have a charge to them. If we gained or lost protons, that would mean we'd be changing the identity of our element, and we can't do that. So to ionize, you can only ever gain or lose electrons. So there's 2 types of ions that we looked at. The first is an ion with a positive charge. That was what we called a cation. So cations are atoms with a positive charge due to an atom losing electrons. So this is really key. You're getting rid of something negatively charged. This will mean you have more protons than electrons inside the atom, leading to a higher net positive charge. The way I want you to try to remember this is that cations, there's my cute little kitty, cations are positively charged. Hopefully that helps you remember that one. Now you have another one, another type of ion. These ones are your negatively charged ions. What we call these are anions. So anions will become negatively charged when you have a higher net negative charge. And how does that happen? An atom is going to gain electrons due to an atom gaining electrons. I don't have as good of a one for this one. The way that I like to think about it is anions are a negative ion, and then you have the word anion in here. So an anion is a negative ion. That's as good as I could get it. But the important thing here is that atoms will ionize. Why are they ionizing? They're doing so to become more stable. They're doing so to become less reactive. So if we take a look at these 2 Bohr models here, we have lithium and we have fluorine. Between these 2 atoms, which one do you think is more likely to lose an electron? And if we're talking losing or gaining, we're only ever talking about the valence electrons. The valence electrons are the ones on the outside, so they're easier, they're more accessible for an atom to lose or gain into. So between lithium and fluorine, which one's more likely to lose? Hopefully you said it's going to be lithium. Lithium has 1 valence electron. Fluorine has 7 valence electrons. If the whole goal here is to fill the octet rule, if the whole goal is to become more stable by having a filled valence shell, fluorine would only have to gain 1 in order to take that electron in and become stable. Or it would have to lose 7 to go down to the n equals 1 energy level. Lithium would only have to lose 1, and then its valence shell, its outermost shell, would be n equals 1, and that's filled with 2 electrons. Instead of gaining, lithium would have to gain 7. That's way harder to do. That's so many electrons. So lithium is definitely more likely to lose. Why? It's more likely to lose because it has less valence electrons. Kind of the general rule is if you have less than 4 valence electrons, you're more likely to lose. More than 4, you're more likely to gain. If you have exactly 4, you're halfway in the middle. We'll talk about what that means in Unit 3. So which atom is more likely to gain? Fluorine. It's way easier. It's close to being filled by just gaining one more little electron into that valence shell. So since elements in the same group, column up and down on that periodic table, have the same number of valence electrons, elements in the same group also tend to produce ions of the same charge. This is really key. This is really important. This is something I also want you to include on your personal periodic table. So if you take a look at this little periodic table right here, everything in group 1, that's this first column right here, has how many valence electrons? 1, because the group number matches the number of valence electrons. So everything here has only got 1 valence electron. It's more likely to lose that electron. How many will it lose? Well, it's only got 1 valence, so it's going to lose that 1 valence. It's going to become stable by losing that 1, forming an ion with a +1 charge. When you write charges, it's typical that you write the sign of the charge first, plus or minus, and then the number. Do you remember when we learned how to count atoms in a compound formula? Like if I gave you something like CaCl2, how many calcium atoms are in this formula? Just 1. And remember, we can find that out because there's an invisible subscript of 1 that's sitting right there, right? So if you're going to write an ion charge, for example, like a lithium ion, if you just wrote Li plus instead of writing Li plus 1, that also tells you that the charge is just a +1. The plus being there indicates that it's an ion in the first place and it just has a charge of 1. So same rules can apply there. Anything that's kind of in this like purpley bluish area here, those elements can form more than 1 possible ion when they ionize. So if you take a look at this example here, iron can form iron +2 or iron +3. We will figure out how to determine what the charge on that ion is from a compound formula in the next unit. Notice the last thing that's important here are these, this group right here, are noble gases. Notice that it says a 0 above them. Why would these things not form ions? The whole point of becoming an ion is to become more stable, to fulfill that octet rule. So why would these things not ionize? They already have filled octets. Everything here is in group 8 and therefore has 8 valence electrons. So this is why we call them the noble gases. They're incredibly unreactive because they are incredibly stable. They already have their valence shell filled. Why would they want to lose or gain? They don't have to. All right, so on your personal periodic table, what I'd like you to do right now is label the ion charge trend, meaning like in group 1, what's the charge of anything in group 1 that would form when it ionizes. Do this for your main group elements. So 1, 2, 3, 5, 6, 7. And then, like I said, skill will come in unit 3 for determining ion charges for transition metals. After this, you are done with your valence electron notes. I will see you all later.